welcome my dear students. In the last class, we have to prove a rank nullity theorem, and we have to discuss two examples based on this theorem. Now, in this class, we define one-to-one and on-to linear transformations. So, let us begin with one-to-one. Let T be a let T be a V from to W be a linear transformation, and U be and the element of the domain. So, this is we have simply said that this is we have a V and this is we have a W is a linear transformation. So, we have this element here and this is the element is here. So, this means every element has a unique image into this form. If we have to like this, we can say that if this is satisfied, this T is mapped into this phase. This is every element of a domain is mapped to the on a single elements of the codomain. Is this. If this is happening is there, then we can say that the transformation T is a one-to-one, or if we have a like this, we have to this is a linear transformation. We have some elements are there, some elements is there. Suppose this is mapped to this is also mapped to this and this. This is clearly this is the two different elements of the domain is mapped into the simple single elements of the codomain. So, then in this case this is clearly we can say that is a not one-to-one, or is called is a many one. A similar like that is a function. This is clearly we can say that is a one-to-one, or we can say that is a one-one. This is in the short we can also say as a one-one function. So, now how can we show that this is a if T from V to V be a linear transformation, and we choose two elements from this domain of this vector V, and now we choose two different element, then this is U is not equal to V. If we have two different elements, then we can choose two different elements here. If these two are not the same, then we have to identify the image of these two elements. This is we have a T of V, this is an element of a T of U, and this is you have a V, and this is you have a U. So, if we take two elements U and V from the domain, and these two are different, that must be implies that image of this is also different. So, this means these two elements should be also different. So, in this case we can say that if this is happening, we can say that the map is linearly a transformation. This means we can simply say that a linear transformation, we take U and V be any be in the domain of a V, the transformation T is one-to-one. If and only if U different from V implies that T of U also different from V sphere. In other way, we also sometimes say that we have to go by the contradictions. We can say that if we have a T of U is the same as a T of a V, this implies that U is equal to V. So, we have to also try to in this by the conversely, if we have to take a contradiction assuming that T of U is the same as a T of a V, then we have also images all those are same. So, U is equal to V is there. So, this means test of a T is 1-1 also we can say that agar T of U is equal to V hai, this implies that U is equal to V also. Okay, so let us begin with the very trivial example of this is the identity linear transformation. You know that T from V to V is defined by every element is mapped to itself. This is we have a for all V belongs to V. Now, we take any two element U and V is the element of a vector space V. Then, because of the identity transformation, this is U, T of U is equal to U, and T of V is equal to you have a V. And now we assuming that T of U is different from we have a we have to assuming that clearly we have to take these two elements TU map to U, TV map to V. So, if we have a U is not equal to V, this is implies that T of U clearly not equal to T of V. So, this means clearly these two are the different maps are here. So, this means we can say that clearly we take assuming that U and V is not equal to 0. If U and V is not equal to 0, because you know that T of U is equal to U and T of V is equal to V, and these two are not equal to 0 means these two are also not equal to 0. So, clearly and then T of U not this has T of U is not equal to 0 means we have can say that the identity transformation is a So this is a 1 1 because the different vector u arrive at different destination of a t of u is not equal to t of v is there. Okay, now we have to try to what about the we have to say the zero transformation. Okay, zero transformation means every vector of a v we have to take it two different u and v are the element of a v. If we can say that t of u is equal to 0 vector there because is a, and t of v is also 0 vector. If we take a u and u is different from v, but you can see this implies that by the 1 1 function t u is should be different of a t of v. We assuming that these two are the different, but you can say that t of u is the 0 is equal to t of v. This implies that you have a t of u is equal to t of v, which is not possible. So, if we take two different vectors u and v, and then we have to just show that t of u is equal to v. So, this means zero transformation clearly arriving at the same destination. So, thus we conclude that the zero linear transformation is not a 1 to 1 linear transformation. Okay, so now we have to just try to some different type of example. Let suppose let t be a linear transformation defined by t of u is equal to u minus v and u plus v. So we take two different elements. So we take suppose we take a u is equal to x y and v is equal to we have a z x. So by the definition t of u is equal to this form, t of v is equal to this form. Suppose we have to assuming that t of u is equal to t of v, this test. If t of u as t is equal to v, then this implies that you have a x minus y, x plus y is the same as a we can say that this is the same as a z minus w and z plus w, and this implies that we can say that x minus y is equal to you have a z minus w and x plus y is the same as a z plus w. Now we have to adding these two, we getting the x is equal to z, and also if x is equal to z, then we have a y is equal to w. So that means we can say that x is equal to z, y is equal to v. So we can just say that u can be written in the form of a you have a x, y, and now x is the same as a z. You can say that x is the element z same as z, y is the same as a w, and this is nothing equal to v. So we are assuming that if t u is equal to t v, then we have to show that u and v are the same. So by the second test, we can say that if we have to assuming that is 1 1, t of u is equal to t u v implies that u is equal to v, then we can say that t is 1 to 1 linear transformation. So this means clearly we can say that this is a our this which is just this we can say that so this transformation is a clearly we can say that this is a linear transform 1 to 1 linear transformation is there. Okay, now we defined another is onto is simply say that we have a this is equal to v, this is we have a w is there, so this is v, then we have a w, we have a this is a linear transformation t, then this map to this means this is the this in this form. So we can say that this is a range of this t is the same as a whole w. Range of a t is the same as a whole w equal to the w. Then there is every element of this. This means this is called is a in this case this is a onto. If we have a like this, we have a v, and this is we have a another w, and this is we have a some element is this. This is mapped to onto to this set. This is t. We have to like this form. Sorry. So this map into this form. This is clearly is we can say they're not onto. In this case, you have a RT is not equal to whole W because this is a subset of a range of a this is the range is completely whole the set of this V, because the range of T is nothing but equal to you can just say is equal to T of a V. V is the element of a V. So this means T of V types is completely whole the set of a this is this form. If in this form this we can say that by this form this is onto, but in this case we have to mapping into a this as a subset of a this. This is a proper subset of a W, and then this RT is not a equal to the whole the W, but is a proper subset of a W. In this case, this clearly RT is not a. In this case, the second one is not a onto map. So clearly onto means we can say that let T from V to W be linear transformation. The transform T is called is onto if and only if every W in arrival vector W there exists at least one V in the start vector of a V. Means we can say that every vector of a W at least one vector from the this is exist here. So at least every vector from the this W set here, there is some at least one vector is belongs to the this set. Maybe more than this is not a problem, but at least one of the vector can be exit into a domain also. So that means we can say that W is equal to nothing but is equal to T of V is there. So W is whole T, W is nothing but is equal to we have a T of V. So that means we can say that this linear transformation is clearly is a onto transformation. For example, we can just say that, or otherwise we can say that as onto transformation. I just said that range of a is T is simply is equal to we can say that the whole of the codomain is there. I just take a example is this form. Let T from R2 to R define as a T of V A into this form. Now T of V, because V is R2, so V is a form of a like this x y. This is the element of a R2. So T of V can be written as a you have a x y, and then you have a is equal to 1 0 0 1, and this is nothing but is equal to you have a x and y. And because this x and y are the for all x and y are the element of R. So this is nothing but is equal to same is a R of T. So T of V is nothing but is equal to what? This is clearly is giving you a completely R2. Whatever x and y we have for every element of x and y is there. So this means we can say that range of T is nothing but is equal to you have a R2. Range of T is nothing but is equal to R2. This is a range of a whole space is R2. So if it is a whole space of a R2, then we can say that clearly this range of a T is R2, means this is clearly map defined into T of V is equal to VA is clearly is a onto transformation is there. So this way can say has a given transformation T is a is onto. Okay, now we consider this. We have to check this example is a 1 1 or onto or not, because we have to map from T from P3 to P2. So we take a standard basis of a P3 is a 1 x square and x cube, and standard basis of this you have a 1 x square. Because we have to check because if we take a this check is a 1 1, that means we have to satisfy this should be is equal to T of V is equal to you have a two different elements giving the different image. So consider we have to take a two different elements, P1 is equal to x plus 2 and P2 is equal to x plus 4. Now if we calculate T of P1 is equal to P prime is equal to you have a 1, and then if we take a T of P1 is equal to x plus 1 का derivative, this is nothing but is equal to x plus 2 का derivative is equal to 1, and again this is derivative of a P2 is equal to 1. So this is nothing but equal to T of P2. So this means we have to T of P1 P2 is the same, but this P1 and but P1 is not equal to P2. So clearly this is not satisfied by the definition. We can say that we have to take a two different images. U is different from V, implies that T of U is equal to T of V. So this means clearly this is a map is clearly is not an onto map. Okay, now it is not onto map. Now we have to try to check as this is a this is not a one-to-one map. Sorry, this map clearly is not a one-to-one map. Now we try to check as this is a onto or not. So let arbitrary element of a P is any arbitrary element of a P we have to assuming is a Q in this form. Now we just take a, because we take a P is the form of a we have a plus I take a P prime plum is the form of a x plus c x square. So this can be written in the form of if you take a derivative of this like this. So this is we have to assuming this is a P prime. Then P is nothing but is equal to in this form, and this is clearly this is the element of a you have to just set it as a as equal to P3. So we take any element of this ax plus ax square b square. This is the clearly element of a P3. and then if we take a t of p, we can get t of p is equal to, you have a t of p is equal to, you have a x plus b by 2x square plus c by 3x cube ka derivative, and then you can see clearly this is equal to a plus you have a is equal to bx plus you have a cx square, and that is equal to, you have a q. So, this means T p is equal to q, and then we have to just say that for any arbitrary element q into p 2, we can find element of if there exists a p, p is in this form, p is the element of a clearly this is the element of p 2. So, T of p is equal to, we have to getting is equal to q. So, that means we can say that clearly this set beta defined by this is clearly is an onto linear transformation. Okay, now we have to prove a very interesting result which is help us to showing that 1 1 is a more simpler. Then we just check if the kernel of this nullity is 0, or we can say the kernel of this linear transformation is 0 subspace, then always T is a 1 to 1. So, we start with this T from V to VW linear transformation into a vector space V2W, and T is 1 1 if and only if kernel of a T is equal to, we have a 0 subspace. So, we can say that let V be any element of a kernel. We have a given, suppose we have to assuming that given T is 1 1, and T is 1 1 means we have to take a T of u is equal to T of V, implies that u is equal to V, or we can say that u is not equal to V, implies that T of u is not equal to T of V. Okay, now we can say that assuming that V is the element of kernel of a T. If V is the element of a kernel of a T, that means we can say that T of V is equal to 0 by the definition of the kernel, and also we can say that we have any element 0 is also, so 0 T of, we know that the T of we know that the T of 0 is also 0. So, this means we know that T of 0 is also 0. So, that means we can say that T of V is equal to 0 is equal to T of 0. And now, because we have to this implies that we can say that T of V is equal to T of 0, but T is giving you have a 1 1. So, this T is 1 1 means V is equal to, you have a 0. If V is equal to 0, and but we have to choosing the V is the element of the this kernel. So, if V is the element of this kernel and V is equal to 0, this means we say that kernel of a T is equal to, we have a 0 subspace. So, it just we can just say that this is clearly 0 subspace. For the previous example, if you take, we have to define from P3 to P2 T of P is equal to P prime. And now we take any element of this, the element of this. For example, this we can check because we show that there is not a 1 1 taking image. Now we take a find the what is the kernel of this. So suppose we have to take any element of a plus bx plus cx square plus d of x cube, and now we take a derivative of this. Clearly, you have a bx, and then if we take a t of p is equal to 0. And then is a derivative of this means we have a can write is in the form of a we take a derivative of this, you have a b plus you have a twice cx plus you have a 3 times you have a d of x square is equal to 0 vector, you have a like 0 plus 0x plus 0x square, and so on. Then we have a 0 of a P2. So, now we have a B is equal to 0, C is equal to 0 and D is equal to 0, but what about the A? So, this means A always is a constant. So, this means we can say that kernel of a T is nothing but is equal to, you have a like this 1 is there. So, kernel of a T is a 1 is there, that means this means kernel of a T is not equal to 0 and this is not equal to 0, then we can say that T is T is not a 1 1. So, in this previous we have to show that take images, and then here also we can by example also this is equal to. Now, we have to pour the converse part. Converse part of this is saying that we have a this is a white. I have to prove this. Okay, now we have to conversely kernel of a t is equal to 0. So we take a two different elements and assuming these two elements are the same. If two elements are the same, this we can say that t of u is equal to t of v, and t from you have a v to w is a vector linear transformation of a two vector spaces. This can be written as a t of u minus t of u is equal to 0 vector, and then because t is you have a giving linear, so this can be written in the form of a tu of u minus v is equal to 0, and because this implies that we can say that u minus v is the element of kernel of a t, and u minus v is the element of a kernel of a t, but kernel of a t is giving you have a 0 subspace. So this implies that we have a u minus v is equal to 0. If u minus v is equal to 0, then we can say that u is equal to v. That is means we can say that. So this is clearly we have to prove that this is clearly kernel of a this is equal to 0. So this means if the kernel of a 0, then we can say that t is 1 1. If t is 1 1, then we also show that kernel is always equal to 0. For example, if we take we have to dash t from R2 to R2, we have to take a t of xy is equal to x plus y, x minus y. Now we try to check is a 1 1 or not. We just minus y. So we take find the kernel. By the definition, kernel of a t is nothing but is equal to, you know that the v belongs to the v such that t of v is equal to 0. So this means we can say that t of x y is equal to you can write in the form of a t of x y is equal to 0 comma 0, and this implies that x y is equal to you have a x plus y, and x minus y is equal to 0 comma 0, and this is nothing but is equal to you have a x y is equal to 0, x minus y is equal to 0. If we have to simplify these two, this implies x is equal to 0 and y is equal to 0, and then we can clearly say that this kernel of this t is nothing but is equal to 0 subspace, and if this kernel of this is equal to 0 subspace, then we can say that clearly this is a clearly this is a 1 1 by this theorem. So t is we can say that 1. So this means we can say that clearly this map define t is 1 1 by the this previous result. Or if we try to check by the definition, we have to just check a t of x u and v. So t of u is equal to t of v, and we take a u is equal to we have a assuming that u is equal to we have a x and y, and v is equal to you have a some x1 and y1. So we can just say that t of u is equal to we have a x plus y, and then you have a x minus y, and t of v is equal to x1 plus y1, and then you have x1 minus y1, and these two are equal only. We can say that x1 plus y1 is the same as x plus y x plus y is the same as x plus y1, and x minus y is the same as x1 minus we have a y1. If we have to simplify these two, you have to getting x is equal to x1, y is equal to y1, and then we can say that clearly if this is happening, we can say that this is we can say that so this is means is nothing but is equal to we can say that x1 is y1. So x plus y, we can say that x plus y if these two equal, then this means we can say that x minus y is the same as x1 plus y1, x1 minus y1. This implies that u is equal to v. So this means we can say that any element sorry, this is clearly we can say that x y is u is equal to you have xy, v is equal to this. So this means these two terms are the same. So u is equal to v also. So this means we can say that clearly this by this example we use by the theorem that the kernel of a t is equal to 0, then t is a 1 1, and also by the we have to using the definition when t of u is equal to t of v, which is implies that u is equal to v. So in both the way we have to, by this theorem is more simpler, we just take a kernel of this, and then if it's the kernel we have to find easily, then we can solve this and then find that if the kernel of this n is equal to 0 subspace, then we can say that this map is clearly is a 1 to 1 map is there. Okay, so now I have to stop today's class here. Today we have to discuss about the rank nullity theorem, and then based on this problem, and this class we show that what is our one to one linear transformation, and what is our onto linear transformations in this some example. And this last we have to prove this very important result, which is very useful in the later of lectures also, when we have using proving some other result, when we have to show that T11 or onto case, because if we have a from here we just clearly by the definition, if you just see the by the theorem, if this is 0 subspace, then the dimension of a kernel of a T is equal to 0. So this means clearly dimension of if we have a dimension of a V is equal to dimension of a range of a T, and dimension of a V is equal to n, then dimension of a range of a T is also n, then we clearly say that if the dimension R is given, then we can easily find the range of a T also. Dimension of a range of T is the same as the dimension of a V. So based on this we have to discuss some more related problem into the next class. We also prove one more important result when we have this dimensions of the these two dimensions are the same. Vector space V and W are the same dimensional vector space. If T is 1 1, then T is onto a range of a T. There is a equivalent conditions also. So in the next class we discuss some one of the equivalent condition, which say that when T is a linear transformation V to W, and V and W are the same dimension, then T is 1 1 and T is onto, and the range of a T is equal to W. All three conditions are equivalent. So in the next class we discuss this theorem, and based of this theorem we also discuss some problems also, and then we have to do this. So thank you very much for this lecture.